Welcome everyone. We're moving into our next realm of integration here. So we're moving into triple integrals. And if we remember back, when we first set up double integrals, the question was we have some flat region on the xy plane and we want to find the volume that sits above that region extending up to some surface that's hovering above the xy plane. So we're going to have a similar question for the setup for triple integrals. And I think the question that kind of helps us wrap our head around what a triple integral is going to be is the mass problem. So let's suppose that we have some three-dimensional object sitting in, well, three-dimensional space. So we have it just kind of sitting here on the x, y, and z coordinate system. And let's suppose that we want to find the mass of this solid. So here's our solid B. And, we have it described here. We're going to start with a rectangular box just to make things easier. And then we'll kind of look at, other cases as well. So we have this rectangular box, all points x, y, z in three-dimensional space, where x is in between two numbers, y is in between two numbers, and z is in between two numbers. So that gives us this 3D box. And the question is, we want to find the mass of this object. And the idea here is we're going to have a density function, rho, equal to f of x, y, z. And f of x, y, z is going to be positive. It's going to be non-negative, so greater than or equal to 0. And this function, conceivably, is going to give us different densities based on where we're looking in our solid. So we want to have some kind of non-uniform, we might have some non-uniform object here where parts over here might be made of some type of material, parts over here might be made of some other material, and so they have different densities. And the question is, how do we figure out the mass of this object? So the idea is we're going to slice this up into a whole bunch of, so we have this one big object, and we're going to slice this up into a whole bunch of smaller rectangles or cubes. So the idea here, to answer this mass problem, is we're going to divide this up into a whole bunch of little sub-boxes. And then for these little sub-boxes, they're going to be so small that we can assume that the density is constant on each of those. So if we have our solid, we slice it up into a whole bunch of tiny, tiny, tiny little pieces. So we're going to have a whole bunch of pieces, and they're going to be really small. And so we can assume then that the density is going to be solid then on each of those tiny, tiny little pieces. And the idea, or how we actually calculate mass, if we have a constant density, so mass is density times volume. So if our density is constant, well then we can just figure out the volume for each of those little pieces, multiply it by that constant density, and we get the mass for each of those little chunks. And then the idea is, well, we add up the mass of each of all those little chunks together, and we get the total mass. So whenever we divide something up into a whole bunch of little pieces and then add up the result, that's integration. So the idea here is to kind of go into a little bit more detail. We have our box, our three-dimensional box here. We have each of these inequalities for x, y, and z. And just like we did for double integrals, we're going to divide each of those intervals up into small little subintervals of equal width. So, we can index if we divide up the x interval, we can index that by I. So we get a whole bunch of little subintervals, xi1 to xi. And the width here, delta x, is just the length of the entire interval divided by how many subintervals. So b minus a over L in this case. We do the same thing for the y, so we could index that by, say, j. So yj minus 1, comma yj. So we get a whole bunch of little subintervals in the y direction, and each of those is going to have the same width, delta y, and this will be d minus c over m. And then same thing in the z direction. So we have our z. Maybe we index these with k. So we get a whole bunch of little subintervals, and then delta z here is just the length divided by how many subintervals. All right, so then we get a whole bunch of little sub boxes. So when we look at these intervals like this, we get the subbox bijk, and that's just some arbitrary one of these little boxes sitting inside our total object here. So then the volume of these little subboxes, well, we can calculate. So if we let's go back. The width of these in the x direction is delta x. The width of each of these in the y direction is delta y. And then in the z direction, it's delta z. So if we wanted the volume of, say, one of these little subboxes, it's just delta x times delta y times delta z. It's just a little rectangular box. So that gives us the volume of one of these little subboxes, bijk. We'll call that delta v. But it's really just delta x times delta y times delta z. And then the idea is, now that we know the volume for each of our little subboxes, for each subbox we're going to pick a little point. So here's our diagram again. Here's our little region all sliced up. And for each of these little boxes, we're going to pick a sample point. So, somewhere inside this box, pick a point. And, maybe somewhere in there. And then we do that for each of the boxes. So we just kind of, we can be clever about it. We can be just kind of random about it. Doesn't matter. But we just pick a sample point from each box. And we do that over and over again. And the idea is we use that sample point. That's where we take our reading. So we look at the material right at that sample point, and we look at the density of the material right at that sample point. So we choose a sample point from each subbox, and the sample point we're just going to call xi star, yj star, and zk star. So this is the point where we're going to actually take our density reading. We look at the material there. And the way we take our density reading is we just plug it into the density function. If we were doing this in practice, we would kind of analyze the material and see what the density of the material there is. But we have a nice formula that tells us specifically what the density is at that point. So we just take our sample point, plug it into the density function, and multiply by the volume. So we get the mass for each subbox by looking at the density. So this is our density, which the subbox is so small at this point that we're just assuming it's constant. And then we have the volume. So this is the mass for each subbox. And now to get the total mass for all the little sub-boxes, we just add them all up. And this is going to give us a triple Riemann sum. So the total mass for our object B is approximately, and then now we're doing a triple Riemann sum, and we're just adding up all of these little mass calculations that we did. So we have our function at our sample point times delta V, and then we're just adding up over each of the indexes. So we have our K summation, we have our J summation, and then we have our I summation. And then the idea is we want to take this to its theoretical limit. So we're not satisfied with just a kind of a crude grid like this. We want to use more and more little pieces. We want to make a finer and finer grid here. And so the final step to get that really fine grid is to take the limit as we use more and more subintervals. So as L, M, and N all approach infinity. And so that gives us the total mass. Not just an approximation. This gives us the exact value for the total mass. So it's the limit as L, M, and N all go to infinity of this triple Riemann sum. And this is what we give. This is how we define the triple integral. And now we're not going to be doing triple Riemann sums. This would be like a numerical type of integration. If we wanted to just get an approximate value here, we would just do the Riemann sum. But the limit process makes this difficult. But we're going to see that. So we have our definition for triple integral. So this is how we're defining the triple integral. Over this rectangular box B, it's just this limit of our triple Riemann sum, provided that this limit exists. And if the function's continuous, then this limit does exist. So if our function's continuous, then we can do the triple integral. All right, so we just need to know that our function's continuous, and for the most part, that's what we work with. All right, so how are we actually going to calculate this? So if we calculate it right from this definition, it would take forever. This is trying to do a single integral from the definition is very difficult, let alone a triple integral. So the way we're actually going to be calculating it is, well, another instance of Fubini's theorem. So we're going to be able to write this triple integral as an iterated integral, where if we have this rectangular box, we can do, the way it's written here, we're doing the x integration first, then we're doing the y integration second, and then we're doing the z integration last. So this is just like what we did for double integrals. So Fubini's theorem really tells us how we're actually going to calculate Fubini, or how we actually calculate a triple integral in practice. So we have our iterated integral here. And additionally, the one thing to note is that we can change the order of integration. So for rectangular boxes like this, where we have just x, the x values are in between constants, the y values are in between constants, and the z values are in between constants, we can set up this in a iterated integral, but we can also, move the order around. We don't have to do x first. We could do y first, or maybe z first. So however we want to do it, maybe one way is a little bit easier than the other. So let's actually try an example just to see how all this works. So we have this triple integral, example 1. We have this triple integral over the rectangular box B, and it's described where x is between 0 and 1, y is between -1 and 2, and z is between 0 and 3. So that's our rectangular box. Now when we set this up, we're going to calculate the triple integral over this rectangular box B. The function here is xyz squared dv. And we want to integrate this. So let's set this up as an iterated integral. And when I'm looking at this, we have a choice of the order of integration. I like the zeros. I think that makes it a little bit easier once we start plugging in. So the way I'm going to do this is let's start with z first, then we'll bop over to x, and then we'll finish up with y. And I might regret this, but we'll see. So we'll do z first. So I'll put on the inner one, I'll put 0 to 3. Then we'll do x. Could have done x first. Then we'll do x. And then finally we'll do y last. So we'll go from -1 to 2. Just because I like the ones with the zeros, just because it'll make evaluation be a bit easier. And then our function here is xyz squared, so that goes in the middle. And now we're ready to start. So we start with the inner integral first. So I'm going to start with our z integral. So we want the antiderivative with respect to z. So the x and the y here are constants. So then the z squared, we just do our regular power rule, and we end up with, what do we get? 1/3 xyz cubed, and then we're going to evaluate this from 0 to 3. And then we have our dx dy at the end. All right, so that's our antiderivative with respect to z. Now let's do the evaluation. So when we do this, the top number goes in for z first. So again, we're plugging in for z here. So the 3 will go in first. So when we get that, we get 3 cubed, but then we have this 1/3, so that's just going to give us 9. So we have a 9xy. And then when I plug 0 in, it all gets canceled off. So we end up with just a 9xy there. All right. Oop. And let's just make sure we're doing keeping the order correct. So now we have a iterated integral in 2 directions. So now we just kind of keep working our way through. So now we do the next inner one, which is with respect to x. So let's see what we get there. So we do our x antiderivative, and again, the 9 and the y are like constants, so we just do our power rule on that x, and we end up with a 9/2x squared y, and we're going to evaluate this from 0 to 1. And as you're doing this, it doesn't hurt. I haven't been doing it, but it doesn't hurt just to make sure you're being consistent. Throw in some x equals and maybe y equals and z equals as you're doing these evaluations, just so you don't forget what you need to plug in for. So we're going to plug in here for x. So I'll plug the x equals 1 in, and then I'll plug the x equals 0 in and subtract. So when we do that, plugging 1 in, we're going to end up with 9/2 times y. And then when I plug the 0 in, I end up with 0. And now we just have a y integral. So now this is just regular integration. Do one more power rule here. And we end up with 9/4 y squared. And then we'll evaluate this from y equals -1 to y equals 2. And if we plugging in the 2, we end up with 9. So we end up with 9/4 times 4. Then we subtract. And when I plug the -1 in, we end up with 9/4. And if we clean this up, yeah, we can leave it like this, really. Perfectly fine. But if we did simplify, I think we end up with 27/4. So this is 36/4 if we get a common denominator. Perfectly fine to just leave it like this, though. And that's the idea. So it's really just the way we calculate these triple integrals, very similar to how we did it for double integrals. And the idea behind the setup for this triple integral is the mass problem. We have some kind of region, three-dimensional object, and we want to find the mass of that object. So the idea is we slice it up into a whole bunch of little pieces. We figure out the mass for each of those little pieces because they're going to have a more uniform density. And then we just figure out the volume for each of those pieces and then add it all up. And we get the density, or we get the mass. And what we're doing there, without even realizing it, is we're doing a triple integral. All right, so we'll try some more of these calculations in class, get a little more practice. But this one's a good one to kind of get going with. So we'll see you then. Bye-bye.